Welcome back to ECE 441A 541A. Relative to homework number 4, somebody sent me an email and asked about, aren't we supposed to be using the final value theorem? And when I said set capital V of S equal to 0, that's really what I was implying. So when you're trying to solve that first problem, I believe, part C, where you're finding the grade that will cause your vehicle to stall, I was really meaning set or use the final value theorem to now allow you to let v of t go to 0. And now you can, with those limiting arguments, you can eliminate some of those variables, and you might want to pay attention to what they're saying relative to the magnitudes or the values of some of those gains or parameters in your system. Meaning you're really looking now at this limit as s goes to 0 of s v of s, where v of s is your velocity that's made up of those two terms, one piece due to the constant input 30 over s, and the other one is this unknown delta d over s that you are trying to solve for. That's homework problem number 1 on homework assignment number 4, and exam number 2 is fast approaching. That's actually a week from Friday, and homework 4 is not due today, it's due on Friday. So trying to keep us on our toes. And a couple weeks after the exam, we will not have class, but you will be invited, if you're a graduating senior, to the engineer's breakfast. Today what I want to do is look at steady state error, because your answers last time weren't correct in terms of what you were thinking might be true as far as the steady state error. You did a good job of finding the settling time, but then that you actually sort of need to, there's a trade-off between transient behavior and steady state accuracy, and we'll try to get through that steady state error material so that you can feel more comfortable performing the homework problems. We'll look at just identifying the steady state error just so that we're clear on what that means, because we may be having this waveform that's actually varying with time, and you're going, did we really reach a steady state? Then we will look at what assumptions were made to obtain that steady state error, and then we'll start calculating some steady state errors. Now, to get us started, I don't know if your eyes, well, that's not too bad. What's the steady state error in this trajectory or in this system? And this is actually one of the responses from the lab. This is spring 1 mass 4 that I generated a few weeks ago. But what's the steady state error? The green line minus the blue line, or the blue dashed line, right? And what do you mean by that? Good. So we need to, when we're talking about the steady state error, we need to make sure that the transient has disappeared, which is that time interval. And then we're really saying, what's the error there? Or you could say, what's the error there? Or what's the error here? If it was an ideal system, those errors would all be the same. Here you can see that maybe they are not quite, but you can identify a steady state error. I didn't label this, but let's say the vertical axis is counts. How many counts is the steady state error, roughly? Just an eyeball. 100. It's maybe a tenth of the way up towards 3,000, and we wanted to get to, or we were wanting to approach 2,000, and maybe we have a steady state error that's 100 counts. That may or may not be acceptable. Is everyone clear on the steady state error and what that means? Even though we have a reference input, which is this dashed line that's changing with time, we still, after a short transient, reach a steady state. And that's the error that we're interested in. Let's see if we can answer the same question for this. This was that figure that I put on the board, I think, last time relative to talking about one of the homework problems. What's the steady state error here? Pardon? 0.6? Where did that come from? You did the homework yesterday. Would you just quit cheating? This is not the homework problem. So I don't think this one's actually 0.6, is it? Where would we identify? So the answer to the homework might be 0.6. I don't know. I don't have it memorized. That may be correct, but this is not the homework itself. This was an example that I was using to help illustrate the homework. But now if you were asked, if your boss now said, what's the steady state error, what would you say? 0.25? Where are you getting that? Okay, so you're looking at the middle part of the decreasing waveform, and you're probably waiting until the transient has gone away. You have a transient every time you switch your reference. Do you see that? Beginning with, you have a little bit of a transient, and then you sort of get into this locked condition where you're tracking this dashed line. The dashed line is your reference. That's where you're wanting this, let's say, robot tool to go. Maybe it's welding. And hopefully these units are small enough that the weld with this tracking error is acceptable. But that's what you would have to be worried about. You might have to make those two lines closer together. If somebody said decrease the steady state error, that's what they're meaning. They're saying make those waveforms lie almost on top of each other, depending on how much the error is. But here, you're getting beyond, you're moving beyond the transient, which the transient is initiated there in the second piece. And now it's sort of up to you to decide, but maybe it's sort of reached a steady state about there. And you might be saying, here is where I will define my steady state error. And now you have to measure that distance. That's the distance between the dashed line, your reference, and where you are actually going, which is the blue curve. That's the steady state error in this example. Is that clear? Now, what assumptions were we making in coming up with those steady state error values? What's the key? Well, this is maybe a vague question, but what is definitely happening in both of those cases? When we kick the system, did the system sort of behave? Did it behave itself? By that I'm meaning, is it stable? It may have overshot. It did have quite a bit of overshoot here, but at least it's stabilizing after a transient. And the same here. It's actually able to track that response or that requested reference input. The very first assumption that we are making is that we have a closed loop system that's stable. So the first one is that the closed loop, the open loop system may not be stable, but the closed loop system is stable. And sometimes we may just say, oh, let's just assume that. But you would have to check that. And how would you check the stability? If you were in the real world, you wouldn't want to just tell your boss, oh, I'm just going to assume this system's stable. Oh, yes, get in the car and it's a stable system. I'm just going to assume it's stable. You would probably want to verify it before you did that, I'm guessing. I'm hoping. If you say you graduated or you took this controls class, right? Now, how would we verify? Or we would need to verify closed loop stability. And how would we do that? Pardon? You would look at the locations of the poles, and the poles are our closed loop system, aren't they? The closed loop system poles, those are in all of our transfer functions. So we would need to check the roots of the closed loop denominator polynomial. That's the first assumption. We need a stable system in order to even think about a steady state error. If our system is not stable, our error is going unbounded, and we don't even have a steady state error to talk about. What else did you assume in thinking about or finding these steady state errors? What had to sort of be finished? The transient. We had to wait for the transient. So that was another assumption that we were making. We are going to say the transients are gone. And now we actually want those transients to be gone before we start changing the reference input. If we change the reference input in the middle of a transient, we're never going to get to a steady state. Is that clear? So we need these transients are gone before we actually change the reference signal. And I'm not sure if that's worded very clearly. I'm finding that maybe my wording can be less clear than I would like it. But let's say this is now our time. Now if our reference input was doing this, let's say this is our reference. We need our transient to be gone. And how do we usually measure a transient? The duration of our transient. To infinity and beyond, right? And what's infinity? 4 or 5 time constants. This textbook uses 4, the 2% settling time. How would we indicate that on this diagram? I need, if I start my reference, let's say my reference was beginning right here. I don't know why I went below, but I did. Now I would want my settling time to be less than where my reference input is trying to change. Otherwise, I'm not going to reach a steady state. So if this is now my length of Tref, then the second assumption is saying, or we need to ask the question, is the settling time T sub s? And you could find that by looking at your dominant poles and finding 4 tau from those dominant poles, assuming that they dominate the response. Is the settling time T sub s less than let's say the time interval changes in the reference input, which I was labeling T sub ref. That's the second assumption, really, that we made, that T settle was less than this changing reference input waveform. Now, in order to maybe compute this steady state error, what are we going to do? Well, we are actually going to say, play on this concept or idea of infinity. If somebody says, compute the steady state error, you could now say, well, let's just assume that very first pulse width is infinitely long, and I'm going to use my final value theorem, because that's effectively the same thing as long as my settling time is less than T ref. I'll get the same answer. Is that making any sense? We're playing on this notion of infinity and how long it is. What we want to do then, the other assumption that we can make in order to compute the steady state error, is to treat the first or any of these time segments, but usually if we're applying the final value theorem, we like to have something that's nice, and we usually start at 0. So treat the first time segment of the reference input, and in this case it was a square wave, but it could be a sawtooth, it could be some other shape. Treat the first time segment of the reference input as if it goes forever. Now let's use those three assumptions to try to obtain the steady state error from these systems we looked at the last time. Let's now find the error steady state for last lecture's systems. And to do that, what we'll do is we'll go ahead and assume that we have our typical closed loop configuration, unity output feedback, our reference in this first set of examples, let's say that's just the unit step, and now we want to find what is E of S effectively for a unit step input. Now, are we satisfying our first assumption? And what was our first assumption? Stable. Was our system stable last time? Do you remember? Or maybe I need to give you, before I start giving you new systems, let's compute this expression for E of S. E of S is simply R of S minus Y of S, since we have no dynamics in the feedback. And Y of S is just G of S, E of S. Or we now have 1 plus G of S, E of S is equal to R of S, or the transfer function now between the error signal and the reference input for this single input, single output case is this 1 over 1 plus G. Now Now, last time we had 3 different systems, and I believe the first one we called AI. Not artificial intelligence, but little a, little I. Maybe it's smart. But this G of S was now a k sub 0, tau sub 0, s plus 1, with k sub 0 equal to 10, and tau sub 0 equal to 1 second. That was the open loop system. It had a DC gain of 10, which we can find by letting s go to 0. And the open loop system had a time constant of 1. If we close the system, the closed loop system was stable. And now let's apply the final value theorem to actually find the time domain value of our steady state error. If we now apply the final value theorem, we can now say the steady state error in the time domain is this limit as t marches off to infinity of e of t, but that's equivalent via the final value theorem to this limit as s goes to 0 of s e of s. And we want the denominator of s e of s to be stable in order to apply the final value theorem. We can now say that's ESS is now the limit as s goes to 0 of s times 1 over 1 plus g of s times r of s, which we were saying was 1 over s. The leading s is canceled by the trailing s in the unit from the unit step. And now we can look at the limit as s goes to 0 of 1 over 1 plus g of s. If we let s go to 0, what's happening to g? Or what is g evaluated at s equal to 0? Yes, in this example, it's k naught. In general, it's the DC gain. And we actually, or you'll see that they may call that the position error constant k sub p. So you may see that as referred to as k sub p. What was our DC gain? For our system, for system AI, we didn't even say what that was until now. Let's now say with tau sub 0 equal to 1 and k sub 0 equal to 1, then g of 0 is k sub 0, which is 10. Which now says that our steady state error for this particular system is 1 over 1 plus k sub p, which is 1 over 1 plus 10 in this case, 1 over 11, which is less than 1/10, isn't it? So our steady state error should be less than 1/10. Do you have an image of what that means? Is it clear if we applied a unit step to this system, what you would be seeing if the steady state error is less than 1/10? You're just waiting for me to show you, aren't you? So I did this a little bit before class, and here is now the step response for that system from MATLAB. Does that seem consistent with what we just computed? We told it, we commanded this system to go to 1 with a unit step. We want to go to 1. Where did it go? A little less. It went to within a tenth, didn't it? It went to 0.909. It's now 1/11th. The steady state error is 1/11th. Is that clear? There is the steady state error staring at us very clearly. For this first order system, it seems consistent. We now have this first order response. All right, so there's the steady state error for system AI. Let's look at system AI, which was this G of S equaling K naught over tau naught S plus 1, with tau naught equal to 1/10 and K naught equal to 1. Now, just with that information, can you tell me anything about what you would expect to happen here? A steady state error that's better or worse than the previous system? And what are you maybe thinking about? What are these systems the same order? Yes. Are they the same type? And we haven't even defined type, but we will start telling or referring to systems as having a type based on how many poles they have at the origin, how many pure integrators they have. This does not have a pole at the origin. It doesn't have an S factor sitting out by itself in the denominator, does it? It's just a pole somewhere into the left half plane. What would you be keying in on? Now we've derived the steady state error formula for a type 0 system. This has 0 integrators in the system, or 0 poles at the origin. This is a type 0 system. The steady state error due to a constant input is this 1/1 plus K sub P. And what was K sub P? That was the position error constant, which is the DC gain for a type 0 system. What's our DC gain for this system? It's 1, isn't it? So now we have 1 plus 1. Now our steady state error is 1/2. What was our steady state error in the previous system? Less than a tenth, wasn't it? So that error in the previous system was better than this one. This error steady state is actually larger. Which of those systems was, well, there is now the step response. And what does that look like? Does that seem consistent with what we had before, or what we were expecting? And now we just have to pay attention to where this trajectory is actually moving to. It's moving to 1/2. And where did we command it to move to? 1. It was a unit step. So we have an error of 1/2. Our steady state error is 1/2. How quickly did this get to that steady state? .25 seconds, right? According to this, let's say, roughly, or if you wanted to, 0.3. What did our previous system, how quickly did it reach the steady state? Not as fast, did it? So we had a slower system, but a better accurate, or a more accurate system in the first case. Now let's look at the third system that we had. From before. And this one I think we were calling system B, or G of S now was 1/S times S plus 1. This one now does have a pole at the origin, doesn't it? This is now a type 1 system. And let's now start to find the steady state error. Using the final value theorem, we can still, the equations are still the same. All we've changed is the g. And if we put that in, we now have this limit as s goes to 0 of s times 1 over 1 plus g of s times 1 over s. This s cancels that s. And now what do we have? Well, if we start putting this in, we need to look at the limit as s goes to 0 of 1 over 1 plus, and g of s was 1 over s plus 1. Well, let's clean that up. We could let s go to 0, and what's going to happen? Well, maybe the limit, it looks like that term in the lower right is going unbounded, isn't it? That's getting big, which should drive our error where? To 0. If we clean this up a little bit, suppose we now say, let's put the denominator over a common denominator. We now have s times s plus 1 all over s plus 1. Or we can multiply both numerator and denominator by s plus 1, and we now have s plus 1 over s plus 1 plus 1. And as we let s go to 0, the denominator's well behaved, isn't it? It goes to 1. But what happens in the numerator? It's 0, isn't it? So our steady state error for this system is telling us that we have a steady state error of 0 for this type 1 system. Is that correct? You guys said this would have the worst steady state accuracy in the last lecture, I think, because it was the slowest, wasn't it? It's hard to remember back to Wednesday, but what we're doing, or back from Monday, this integrator in our open loop system, or the pole at the origin, that integrator in our system g of s is helping to drive the error. It's integrating the error away. If there's any error between the reference and the output, that integrator is now saying, I need to drive you to 0 so that I'm a stable system. The integrator in g of s helps drive the error to 0. What's the DC gain of this type 1 system? That's what we were using to sort of say how small or large our steady state error was for a type 0 system. Now for a type 1 system, that pole at the origin, we don't have a DC gain, do we? It's unbounded. Do you see the Bode plot of this transfer function? If you had to sketch the Bode plot of this transfer function, do you remember what a pole at the origin does, Bode plot wise? It's always sloping, isn't it? It's always sloping, and it's sloping down at minus 20 dB per decade. That means it's really, really high when you get to the North Pole, if that's where we're going. because we never get there, do we? The frequency axis just goes and goes. 0.00001 for a frequency on a logarithmic scale in our Bode plot. It's just going up and up and up. And that's consistent with what we're seeing here. It's really not defined, or we could say unbounded, and that's producing this zero error, which if we look at it, if this is the right one, here is now the step response of that type 1 system. Type 1 meaning it has one integrator, or one pure integrator, one pole at the origin. What's the transient of this system? What's the settling time? You remember last time it was 8, wasn't it? That looks about right. What's the percent overshoot? Just, yeah, maybe a little less than 20%. That's maybe close enough for, back of the envelope. You're wanting to kind of have this stuff available to you rather quickly. So now we have an overshoot. Those type 0 systems, which were first order systems, didn't have any overshoot. Now we have a little bit of transient behavior that maybe we're okay with, maybe not. It's slower, but what's our steady state accuracy? It's much better, isn't it? It's 0. So now if we had to compare these signals or these systems' behavior, this one, B, would be the best steady state accuracy, and which one is the worst? The middle one, which had a steady state error of 1/2. And do I dare try to find that from before? Now we're playing with fire here. Here's where we ended up last time, and we were trying to judge the best. Well, we just found out that B was the best, and which one was the worst? A2, right? So this is actually the answer which is not in the notes, so you may have to add that into the notes if you have notes from last time. But after our discussion of transient behavior and settling time, you were sort of thinking maybe just the opposite, weren't you? The star is indicating where the class was sort of voting last time. There's this trade-off between transient behavior and steady state accuracy, and that's something that I hope that you start to feel a little bit more comfortable with. What have we done so far with these responses? That was a pretty vague question. But we commanded these with what kind of a reference signal? A step. All 3 of those were excited by a constant input, and that constant in this case was a unit step. And we were able to infer or learn something about the steady state error. Well, what would happen if we now said, oh, well, maybe we have a robot arm with a tool on the end of it, and we need it to go up this sawtooth pattern because we want our weld to be following that particular shape, and we want it to track that way. Now we're asking, what happens if we apply a ramp input? What if we now said, let's go back to some of those earlier systems, let's say a first order system with a DC gain of K sub 0, we can still think about the steady state error, can't we? And the steady state error is still We haven't changed the block diagram whatsoever. We're just going to change the reference input R. This is still 1 over 1 plus G of S times R of S. But now if we want a ramp, what do we want capital R of S to look like? Yes, so now if you heard that, if we said, oh, let's let our ramp be some slope of A with T, then the reference input in the frequency domain, R of S, is now this A over S squared. Now what happens if we have our type 0 system trying to respond to a ramp? Well, let's see if we can learn anything from just analyzing it with the expression for the transfer function between the reference input and the air. This is now 1 over 1 plus k sub 0, tau sub 0 s plus 1. And if it was a unit ramp, capital A would be 1. Now let's clean that up a little bit. What do we have? We can now push that A onto the numerator. We also are going to have that factor in the denominator of our denominator, which we're going to move upstairs. We have the S squared coming from the ramp, and now left over we have tau sub 0 S plus 1 plus k sub 0. Are we okay with that algebra that I just did? I simply found a common denominator in the denominator, moved that denominator of the denominator upstairs in the numerator, and I now have my ratio of polynomials for my E of S signal in the frequency domain. What's that look like in the time domain? Can you do that? Let me put my glasses on so that I can see all of your heads shaking in the right direction. You want little e of t. Now, don't get too nervous. This isn't a big deal, actually, is it? What's in parentheses? A linear factor, and in the denominator, I'm sorry. In the denominator, what do you have inside the parentheses? You just have a linear factor. A pole, a real pole. And preceding that parenthesis in the denominator, you have S squared, 2 roots at the origin. Now, do you envision a partial fraction expansion of this? Can you envision that? No? We now have a repeated factor. We have S and S squared, so we have to put both of those in the denominator of our partial fraction expansion. We have an alpha 1 over S plus an alpha 2 over S squared plus an alpha sub 3 over, and if we wanted to, we could factor out this tau naught, and then we have an S plus 1 plus k naught over tau naught, and there's our pole staring at us. Our pole is at minus the quantity 1 plus k naught divided by tau naught. And as tau naught, as the time constant of our open loop system gets smaller, that pole gets further out into the left half plane, or faster. But this now says that we have a denominator here of S plus a real pole. What's the air signal going to look like in the time domain? What's the inverse Laplace transform of alpha 1 over S? alpha 1, isn't it? That's just a constant. What's the inverse Laplace transform of alpha sub 2 over s squared? We're not having to find these alphas. A calculator can find these alphas. This is just alpha sub 2t, isn't it? And what's the third term? E to the minus sigma t, whatever that is, but sigma here is just this 1 plus k naught over tau naught. If we increase the DC gain, the k naught, that gets bigger. If we decrease the time constant, sigma gets bigger. That pole moves further into the left half plane, but what's that going to do as time evolves? That third term. It's going to vanish, isn't it? What's the first term going to do? Just give us a constant. What's the middle term doing? That's our problem, child, isn't it? It's doing what with time? Going unbounded. It just keeps growing and growing. What's that saying? You commanded this type 0 system to try to track a ramp. And if you just kept trying, it's like the little engine that couldn't, right? It can't keep up. Oh, I'm so sorry you guys can't play along at home, but I'm now growing my one trajectory, my reference trajectory that I'm telling this system to try to track. It's going like this, and what's happening to the actual response? Has a transient, and then it, do you see the error growing with time? That's what's happening for this type 0 system. It doesn't have enough in it to stay up with that reference signal. So we would have an infinite error, steady state error. No need to even worry about it. The error grows. Here's our error. And that's just growing with time. What about our type 1 system? Does that do any better? Is error steady state bounded with that beast, and we're assuming now still a ramp, let's say a over s squared. What's going to save us is that pole at the origin. That pole at the origin is going to be the saving factor here. Is the closed loop system stable? Closed loop system doesn't really depend on the input, does it? Closed loop system is stable. And what's our steady state error? We can find that just like we've done. That's this 1 over 1 plus g r. Now we just have to be a little bit more careful with the analysis. Using the final value theorem, there is our expression for this steady state error. With this particular system and it being a type 1 system, now what do we have? Well, we have this leading, just canceling one of those. The other s is going to be distributed across, well, it depends on when you want to distribute it, but let's say that we distribute it now. Now we're looking at the limit as s goes to 0 of 1 over s plus 1 over s plus 1. But that's now the limit. If you didn't do what we just did, if we didn't do it quite so quickly, that's now the limit. What's happening to this piece right here, this s, the first s in the first term of the denominator, as s goes to 0? That goes to 0. But what's left is this 1 over s g of s. That's really what was left over, and we actually call that the velocity gain constant, case of v, is the limit as s goes to 0 of s g of s. And because g of s had an s in the denominator, if you look at what this is doing, as s goes to 0, we have 1 over 0 plus 1 over 0 plus 1. Is that okay? That's 1, isn't it? And our velocity gain constant is this case of v, which is the limit as s goes to 0 of s g of s. And if that's really big, then our error due to a ramp is going to be small. Here is what our error due to a ramp looks like for this particular system. What's our steady state error? Do you see the transient? And could you now read off the steady state error if this was on an exam? Could you estimate what that is? And I'm hoping you'll say yes. We'll pick up somewhere related to this on Friday. But I hope this gives you the information you need to do your homework.